Please welcome Broadcom Senior Vice President and General Manager, Core Switching Group, Ram Velaga.
Hi, good morning. Hopefully you all are enjoying Happy Prague as much as I am. It's been a beautiful city. It's actually been great to see a lot of friendly faces around in Prague. Today, you'll probably hear a lot about sustainability. I was looking at the agenda. There's a lot about quantum computing. In between all of this, what I want to leave you with as you leave today is the key to enabling compute and open compute as you know it is all about open networking. And nothing comes closer to open networking as networking that's based on Ethernet. And I want to share with you some of the advancements in Ethernet, especially when you think about this whole world where you're hearing a lot about generative AI and a lot of ML AI, how Ethernet and Ethernet-based networking is enabling the next generation of compute. One of the things that you've probably heard about for the last many years is this notion of Moore's law coming to an end. It's something that we've enjoyed for the last 2 decades, right? That every 18 months, the transistor density was going to keep doubling. And the doubling of this transistor density allowed compute and the acceleration of compute like you've not seen before. Now, a few things that are starting to happen in Moore's law. First, as you went from the 16 nanometer process nodes to the 7 nanometer process nodes, you got about a 35% increase in performance. Now, when you look at going from 7 to 5, you're getting less than a 10% improvement in performance. Not only that, another thing that's going on is the cost per transistor is actually going up. When you go to TSMC and ask them how much more expensive a transistor is, when you go to a 5 nanometer versus a 7, it's actually 20 to 30% more expensive. And another secret that nobody generally talks about is the maximum size of the chip that could ever be built continues to be the same, which is about 800 millimeters square. Right? So now think about it. The transistors are not getting any more efficient. The maximum size of the chip that you can build is pretty much remains the same. So how do you actually continue to scale compute, right? And for the last about 20 years, some of this problem has been solved. Historically, you've probably heard about mainframe computing, where you had these very largely integrated, boxes with large CPU, monolithic applications running on a mainframe computer. But starting in the 2000s, you've seen the likes of Google, the Google Clouds, the Metas, and the Amazons, and everybody else. What they said is, look, it doesn't make sense to build one large computer. It's better to actually build a computer by taking a bunch of smaller pieces and then distributing them, right? And so the whole idea of a cloud computing started to evolve. And when you think about a cloud compute today, it's a massive data center with tens of thousands of servers, if not even hundreds of thousands of servers, all acting as one. Right? So as the hardware started to become available, then you started to see the whole, the software started to change. Before you had large applications which were monolithically written. Then you started to see the whole idea of Kubernetes and containers where applications actually scaled up, by scaling out. Not necessarily by writing one large monolithic application, but they really were scaling out. So you started the evolution of the whole scale-out architecture. Now, if you think about the scale-out architecture, and it's hard to see it on this picture, what enabled the scale-out was effectively the network. And I will show it to you in the next few slides, how network enabled the scale-out. But without the scale-out that's happened, almost all the applications that you experience today, right? Whether it is the Google search or being able to spend a lot of your time on TikTok or social media, all the things that you shouldn't be doing but you keep doing, it's all enabled on these platforms, which are all based on distributed computing. Now, about 20 years ago or so, Oracle phrased this term, which actually Sun, my apologies. Sun phrased this term that says, network is the computer. It didn't actually make sense to me then what people meant by network is the computer. But when you actually think about it now, when you think about what the computer is, it is nothing but a whole bunch of distributed compute, all connected over a single large fabric. Then it starts to occur to you that without the network, there's no such thing as a large-scale compute. Now, There's different ways to solve this problem. Today, you hear these concepts about chiplets, right? Taking a large chip, breaking it down into smaller pieces, and then connecting them over UCIs and other kinds of interfaces. But they can only get that big because a PCB is going to limit the size of how large a chip you can build. So if you really want to build the largest compute in the world, how are you going to do it? You have to put it over a network, right? And when you think about the size of these networks that you can build, they could be very, very large. You can easily attach about hundreds of thousands of servers in a large data center that's about the size of a football field. And over a period of time, there's a lot of networking technologies that competed to essentially be the winners. There used to be ATM, there used to be CIDI, there used to be FIDI, but over the last couple of decades, the only one Ethernet technology that continued to survive and flourish is Ethernet. Why Ethernet? It's very simple. It's open, standards-based, completely interoperable. More importantly, there's a ton of competition. Every day you look around, there's another company in the Ethernet space trying to make Ethernet networking. And all of that has essentially accelerated the pace of Ethernet innovations. Today, to give you a perspective, on an annual basis, there is 600 million Ethernet ports sold. Okay, somebody, last time I presented it, they said, well, what does it mean? What does 600 million Ethernet ports mean? There's about 150 million babies born on the planet every year. You can give them 4 Ethernet ports for everybody who's born to give you the context for what 600 million Ethernet ports means. That is how ubiquitous Ethernet is, right? When you actually think about your cars, not a long time ago, you had proprietary technologies on your car connecting all the infotainment systems, all the sensors, the data collection mechanisms, and so on and so forth. Today, it's all based on Ethernet, right? If you go to factory automations, the factory automations used to be based on proprietary technologies, all going towards Ethernet. That's how ubiquitous Ethernet is. And then you say, why is Ethernet that successful? That's because, number one, it's open, standards-based, plug and play. And more importantly, because of competition, it drives a lot of innovation. We at Broadcom are in the Ethernet business, and we can't stand still because there's so many companies competing with us in this space. So the only way we can actually be in business is to relentlessly execute, right? You innovate and you execute. And I want to give you some perspective on what this execution does or this innovation does. Over the last 10 years, every 18 months, we've doubled the bandwidth of the chips that we've put out there. Okay, and to put that into context, I know some of you here are from the service provider, businesses, and you're building large telco networks. About 10 years ago, if you went and asked somebody to give you 128 ports of 100 gig, okay, 128 ports of 100 gig, they would have given you a list price of $1 million, and it would have consumed 20,000 watts of power. Okay, 10 years ago, $1 million. 20,000 watts of power. Today, you can get 4 times the performance. Instead of 128 ports of 100 gig, you can get 512 ports of 100 gigs, okay, for less than $10,000. For everybody who's complaining about inflation, bet on Ethernet, okay? We will take care of it. So you can go from $1 million to $10,000, but more importantly, when you think about sustainability, what consumed about half a rack space and about 20,000 watts of power, today is 500 watts of power, okay? So it pays for itself to rip out all the existing networking infrastructure you have today and replacing it with the latest, because the amount of money you're going to save on power and the reduction in the carbon emissions is bar none, right? Just think about it, 99% reduction in the cost and 99% reduction in power over 10 years. And this relentless march is going to continue. We have 50 terabits today. Most people can actually predict what our roadmap is going to be 18 months from now just by looking at this slide, right? That's why Ethernet. Now, however, while Ethernet's been great for the last 10, 20 years, it's not without its set of challenges, right? When you think about cloud computing, it was all based on taking CPUs and distributing these CPUs over these large data centers. But now when you actually think about this whole idea of ML and AI, everybody talking about accelerators and GPUs, there are thousands of GPU cores on a single die. And that's not sufficient to build a large ML AI training model. You start to hear about how it takes billions of dollars to build these training models. That's because it requires tens of thousands of GPUs. Some of these clusters which are being built today, this year, are probably going to be about 32,000 GPU clusters, each having thousands of cores in them. And chances are these things are going to cost hundreds of millions of dollars to build, right? That's the amount of infrastructure that's going to get built by one company, and there's a rat race going on today for multiple of them all trying to be ahead of each other in these training models. So when you start to think about these training models that scale to the levels that we are talking about, network becomes even more of a bottleneck than it has ever been in the past. About 6 months ago, or maybe 5 months ago, Alexis from Meta presented this slide. And it basically said, the network I/O is the foundation for these new recommendation models. And this was even before generative AI started to be talked about, right? And what it shows here in these different blue charts is the different kinds of workloads. M1, M2, M3, M4, it's probably their code names for different models. Don't ask me what they are. But if you actually focus on the numbers here, what it shows you is in some cases, 57% of the time it takes to complete, whether it is a training model or an inference model, is spent in the network, right? If I told you, just to put that into perspective, you work 8 hours a day, that you're going to be spending about 60% of your time in a day, right, in the traffic every day. That's about 5 hours you're going to be spending in traffic. You won't like that. That's exactly what's going on here. That's about 50% of the time is being spent in networking, where the GPUs are waiting for the information to be traversed over the network, right? And so when you look at that and say, why? What is the problem in the network? It's not about the problem in the network, but what's happening is the GPU workloads or the AI workloads are very different from the compute workloads that we knew of before. In the case of the compute workload, it was small packets, small flows, multiple machines talking to each other. In the case of GPUs or AI machines, there's very, very large flows. What I mean by a very large flow is the communication between one GPU and another GPU lasts for a very, very long period of time. And a lot of data is being transferred between those two GPUs for a long period of time. Now imagine this. When you have very, very long communications, the best way to think about this is you're on a highway, let's say you're on the Autobahn, and you have 4 lanes, and you could go unlimited speed on all these lanes. But what if all the cars decide to stand behind just one truck in one lane, and all the remaining 3 lanes are sitting empty? What ends up happening? Everybody slows down, right? So the nature of the traffic flows in machine learning are very different than how you've seen cloud computing before. And that actually puts a whole bunch of new stress in the network, and very different than what we've seen in the past. And this picture is really what it's trying to show you, different ways that you can get stuck behind somebody else, and you get really backed up. It's like standing in the line, somebody is waiting to order something in the restaurant, and they're asking 50 questions, and you're sitting in the back sitting very, very hungry, right? That's what it feels like. The whole network is getting blocked up because you have 1 or 2 workloads that are holding everybody else up. So then you look at this and say, what can we do? And here is where I'd say just the innovations in the Ethernet are going to keep happening. Either it's going to be us, Broadcom, doing it. If you're not going to do it, somebody else is going to do it because it's open standards-based, and somebody else is going to win. So what we've just actually announced yesterday was perfect timing, was this chip. It's called Jericho3. It's hard to probably see it, but I can tell you it's pretty exciting. It's got tens of billions of transistors. And what it tries to do in this chip is address some of the problems that we've seen in the last couple of slides, is being aware of the fact that the traffic flows in an AI environment are very different, and essentially being able to build a very large cluster. Today, we can actually build a cluster that is 32,000 GPUs, each at 800 gigabits of speed. Okay? If you try to actually do the math, that's about 25 petabits of data transfer that you can actually do in a very, very large cluster. You can probably look at this and say, does somebody need it? Actually, people are calling and saying, hey, I wish we had this now, not 6 months from now, because by the time we actually get samples out, it goes to production, it takes about 6 to 9 months, sometimes about a year. But that's how much demand is there for chips like this to address these problems, right? And to do that, there's a bunch of things that we do. And I'll give you, just one example of how we do it. Like I gave you the example when you're on an Autobahn, and there's 4 lanes, and essentially you're all stuck behind one traffic. What we do is perfect load balancing. For example, the switch is very, very aware when looking at a communication from one GPU to another GPU and saying, look, if you want to go from GPU A to GPU B, don't take path 1, but take path 2 or path 3. So we're constantly aware of what's exactly going on in the network and making sure the network at all times is properly utilized, and you don't have a lot of underutilized infrastructure. Right? So there's a lot of innovations there. What does this all lead to? And I'm going to take a little bit of a comparison to InfiniBand. Here's what happened about InfiniBand. How many of you probably heard about InfiniBand in the past? Good number of you, and you probably are hearing about it more now than you've heard about it in the past. It was a technology that most people thought was dead. To the brilliance of NVIDIA and Jensen, he clearly identified that networking is the key to how GPUs are going to scale. So Mr. Jensen bought Mellanox. Mellanox was the only company in the world that was building InfiniBand as a technology. Now, when you go to NVIDIA and try to buy a GPU system, they'll try to sell you a DGX, which is a completely vertically integrated system with InfiniBand in the backplane. What's the problem with it? The problem with it is it starts to look again like a mainframe. So we are back 50 years ago on how computers used to be sold, large mainframes. Instead, what is it that you want to do? You want to be able to build a distributed compute over a distributed open compute fabric like Ethernet. And then what will the InfiniBand guys tell you? They'll say, well, the Ethernet performance is not good enough. It sucks. Excuse me. But the reality is when you actually build these very large fabrics and look at how fast Ethernet is actually innovated and the bandwidth that's available on Ethernet, these are open benchmarks that show you that Ethernet actually achieves at least a 10 percentage performance points advantage over InfiniBand. Now, for most people, you say, hey, 10% is not big enough for me to sway my decision one way or the other. But let me actually give you some perspective. When you build a 32,000 cluster, you're probably spending at least $1 billion on that cluster, 32,000K cluster. It's about $1 billion. The cost of the networking is less than 10% of that. Okay? So if I can make your $1 billion infrastructure 10% more efficient, the network actually pays for itself. This is what I call infinite returns on investment, because anytime you put some amount of money, immediately you get your money back, and you can do it every day, every other day. That's a lot of return back, and that's exactly what Ethernet gives you, which is it cuts the cost of the infrastructure by improving your efficiency by at least 10%. It's open, and if you don't like what we do on Ethernet, go buy it from somebody else. It's not just a single vendor that's making Ethernet available. There's a lot of competition in Ethernet. So what I'd like to leave you with is, if you're thinking about building anything which is HPC or an MLAI infrastructure, please ask the question, why not Ethernet? Or forever, you will be stuck with a vertically integrated solution. Right? Now, as we're doing this, obviously, we're doing this all with sustainability in mind. As I've given you an example, 10 years to now, 99% reduction in power, 99% reduction in cost. But even between our two generations, 18 months ago to now, we have a 40% reduction in power between the previous version of Jericho chip that I have in my hand and the one that we currently have. Not only that, some other data points I want to share with you. About 10 years ago, if you wanted to go buy an Ethernet switch or a router, you paid about $1,000 for a gigabit Ethernet port, and you paid about $100 for a gigabit Ethernet optic, especially for those of you who are in the telco market probably realize that. And what used to happen, the networking OEMs would give you a pluggable Ethernet optic for free if you bought their switch. Today, actually, the math is inverted. You can go buy a 100 gigabit Ethernet port, at the silicon level at least, roughly around $10 a port. Okay, $10 a port for a 100 gigabit Ethernet port. But if you try to buy the optic is about $100. So actually the math has inverted, where the switch used to be 10 times the cost of the optics. Today the optics are 10 times the cost of the switch. Why? Because the switches took advantage of Moore's law, and you rode the price benefits of cost reductions by successively going to the next node. But optics never never took advantage of silicon capabilities. They're always manufactured manually, right? So because of that, today optics are one of the largest costs in building a large-scale computer system, in being able to connect all of these things. So a lot of what we are focusing on the Ethernet is, how do you avoid going to optics? Can you actually get more and more mileage out of the copper? Okay, that's one. Two, if you have to use optics, can you reduce the active components in the optics, which is, can you reduce a lot of the DSPs and try to go as fewer components as possible? And number three, if you can't do one and two, the other thing that you could do is, why don't you bring the economics of silicon into optics, and that's called silicon photonics. So a lot of what's happening in the Ethernet space in terms of innovation is, one, try to extend the reach of copper. Two, if you have to use optics, reduce the DSPs which are used in optics. Number three, if you have to use optics, then try to see if you can get the benefits of silicon photonics, right? So a lot of this work is going on. That's actually another area of advantage for Ethernet versus InfiniBand. You try to buy InfiniBand, they limit the cables that you can buy, the distance of these cables, who can sell those cables, and what they charge for the cables, right? All of this, again, you want to be on an open ecosystem. So to that, we're very, very thankful for what OCP does in being able to provide the platform for technologies like Ethernet to be able to flourish. We have made contributions to OCP over the last many years, starting with our chips like Tomahawk 5, specs that we have submitted for how you build very large-scale routing topologies, and most recently, how you build systems using the Jericho3 chipset. So thank you very much for your time. I appreciate your interest in Ethernet, I would say, and I would leave you with the following, which is the largest compute systems in the world are being built with Ethernet. So as you look forward, thinking about deploying anything which is ML, AI, GPUs, and accelerators, please ask the question, why not Ethernet? And do not get caught up in proprietary InfiniBand technologies. Thank you.